Dear participants, ladies and gentlemen, good evening. I'm very delighted to have this opportunity to share with you the status and trends of manufacturing technology for high-performance bamboo screenbar. Four parts of my presentation. First is background of high-performance bamboo screenbar. Second, properties of high-performance bamboo screenbar. Thirdly, engineering application of high-performance bamboo screenbar. Fourthly, international communication and the prospects of the bamboo screenbar. Part 1, background of high-performance bamboo screenbar. Some R&D background. Back in 2020, the timber raw material consumption in China reached 100 million cubic meters, out of which 50% is depending on foreign imports. Another background was in 2017, all commercial logging of natural forests was banned. So the external dependence of timber in the near future would be 75%. Against this background, how could we satisfy the needs of domestic timber consumption? This is a big challenge for the scientists in China. On the other hand, China boasts the richest bamboo resources in the world, having 7 million hectares. And with a large DBH, bamboo reached 2.51 billion. Bamboo industry is developing very rapidly. In 2021, the output of bamboo industry reached 350 billion RMB yuan. So how could we replace timber by bamboo resources? By doing so, we can use bamboo to partially replace high-quality, broad-leaved natural forests. This is a huge potential area. The high-performance bamboo screenbar is to use rich bamboo resources in China. And by doing so, we can meet the gap of lacking of timber resources and realize low carbon and green development. So by using high tech, we can produce high-performance bamboo screenbar. Then the shortage of hardwood problems will be resolved. High-performance bamboo screenbar in China is also called bamboo steel. We have two categories of bamboo steel. Back in 2016, it was featured in Sympodio bamboo. The species was called Mucinocalamus as the raw material. It has high strength, high weather resistance, high dimensional stability, and it's very environmental friendly. In the second stage, now we are using a diversity of bamboo resources. So we have both the definition of a bamboo steel in the narrow sense. Narrow sense was only referring to the Sympodio bamboo. In the broader sense, it refers to a large variety of bamboo species. The characteristics of bamboo steel are as following. They are controllable in terms of performance, adjustable specification, and designable structure. Why we call high performance bamboo scrimber, bamboo steel. Actually, a decade ago, when we developed this by using new Cyanocolumous species, we believe the specific stiffness of this bamboo was very good. We tried to use this to manufacture blade of wind turbine. But before using the bamboo steels, the previous species were glass fiber. But now we are using BFC. We got the name inspired from the traditional glass fiber reinforced composites. So we call it high performance bamboo fiber-based composites or bamboo steel. Now the BFC is widely adopted by the designers. You can see the density of bamboo steel is 1.1 and the GFRC is 1.5. But talking about specific stiffness and modulus, the bamboo steel is much higher. 4 stages of bamboo steel development in China. In 2004, China's bamboo industry was suffering the bottleneck. In this context, the Chinese Academy of Forestry started the research. After 6 years study under the governmental's 863 research program support, we started the library pilot and production trials in the Hongya Zhuyuan R&D company. We produced the first bamboo steel production line. In 2012, we realized the mass production and also scale application in Anhui, Sichuan, and many other enterprises. In 2015, the bamboo steel was awarded as the National Scientific Advancement Award and being used in Anhui and Sichuan provinces and had a promising future since then. Coming back to the manufacturing process of bamboo steel. When we talk about bamboo scrimber, we should start the discussion of wood scrimber. And based on the original bamboo scrimber, we developed a bamboo steel. So this is a round shape bamboo comb through the screaming roller. We made this into the fiber-based board, 1.2 meter times 2.4 meter. So this is very suitable for large-scale panel production. So you can see this is a step is to destroy the surface of the material. By the destruction of the surface, we can improve the utilization rate of the bamboo resources to 90%. This is an innovative technology by China. We have already applied 40 plus patents and 4 international patents and 3 EU patents. So you can see it's a very comprehensive patent and IPR protection. This is the bamboo steel creation team. Mr. Wang Zhong is the first company's founder who ever used bamboo steel. During the dissemination phase, designer Wang Gang played a vital role, including other team members. They all made their due contribution to either the creation or the application of the bamboo steels. As I mentioned, bamboo steel is not narrowly based on the new Cynocalamus species anymore. We also use other species varieties. There are 22 bamboo species. We made comprehensive tests. For example, from Yunnan province, Bambusa Burmanica gambo, you can see the MOR, MOE, very good. And we also use the Neo-Cynocalamus from Sichuan province. And the most popular one is Moso bamboo. But MOR for Moso bamboo is only 185 MPa. So from these slides, you can see Moso bamboo comparing to other species on these slides, like bamboo soidea and Philostachys rutila. With regard to MOR, Moso is not that good. On this page, Acanthus ilicifolis and Bambusa trongi, with regard to MOR, are also better than the Moso bamboo. The Philostachys bizeti and the Dendrocalamus and Bambusa dismuluta McClare, MORs are far better than Moso bamboo, all these bamboo species. This slide shows you in Fujian province. Fujian province major species is a Cynocalamus oldhammy. You can see MOR reached 235, and the rest of the bamboo species MOR is around 150. So those were the general overview of MOR of all the 22 bamboo species. Second part, I want to talk about the properties of high-performance bamboo scrimber. First is bending strength. This is made out of Neo-Cynocalamus. This is for the wind turbine blades. MOR can reach 364. The average hardwood MOR from Southeast Asia was only 80 MPa. So you can see these bamboo steels bending strength is around 4.6 times than that of hardwood average. This is the tensile strength. This is the bamboo steel's tensile strength is 2.2 comparing to average hardwood. Compressing strength, again, bamboo steel is 194 MPa. This is 3.2 times than the hardwood. Shear strength of bamboo steel is 2.1 comparing to average hardwoods shear strength. There's another indicator very important. If we want to use bamboo steel into the wind turbine blade, there is a very important feature we should look at, that is fatigue performance. You can see we use laminated wood steel products versus bamboo steel. After more than 1 million rounds of tests, you can see the fatigue performance of bamboo steel is the best. bamboo steel has also excellent anti-mold feature. In the South China, we had the anti-corrosion resistant test, both in the field and in the lab, and soil bed test. You can see the anti-decaying bacteria integrity index is 9.5. The overarching indicator can reach the mold resistance of grade 1, that is a top grade. Meanwhile, it has a very good mildew resistance. The average value of mildew is 0.17, reached the grade 2 level. The termite resistance through the lab test, field bearing test, and erosion test, we got this conclusion. The normal bamboo materials, normal timber materials was being severely damaged by the termites. But you see, bamboo steel is almost intact, especially from this photo. The normal scrimber of bamboos are being eaten by the termites. But you can see on the right-hand side, bamboo steel is almost intact, not being damaged at all. And also it has very good fire resistance, reached grade 1.
And finally, we have a very good strength of this product. And we're using 100 degrees Celsius plus 28 hours water boiling test. And you can see that 100 Celsius degree, 28 hours, the thickness inflation is only 2.8%. After 63 degree, 4 hours water immersion, thickness swelling is only 1.2%. 20 Celsius plus 24 hours of immersion, only 0.7% thickness swelling. From these data, it's clear that bamboo steel has really good dimensional stability. And as a new emerging material, we also see multiple other properties. For example, it can be connected, it can be peeled, it is sand planing, finishing, joinable connections, and it can definitely meet all kinds of processing needs. It can also sawable. And thirdly, I want to talk about the engineering application of high-performance bamboo scrimber, basically the user cases. On this picture, you can see that in 2010, for our first batch of bamboo steel, we developed the blades for wind turbine. The first 1.5 megawatt level bamboo scrimble turbine blade, it passed the static load testing. We are doing a static load testing. And this one, you can see 3 blades as a set, already painted and coated before installation. For every blade, 6.2 tons and 4 tons are made by bamboo steel as a scaffold. And this picture I want to show you for this material, outdoor settings, some waterfront walkway, and this is in Guangzhou Haixing village. Is a landscaping project using bamboo steel. And also broad walk at Boyang River, 5,000 meter waterfront broad walk, the longest waterfront broad walk in China. And also this is in Beijing Expo, Garden Expo, by using bamboo steel to make an installation, a curved landscape installation. And this one, I'm showing you the so-called the eye of the city in Chengdu, Danjingge Pavilion. The whole building is made by the bamboo era's bamboo steel. The whole building is built in China. It is a major tourist attraction. And this one you can see, it is also in Sichuan. It is a landscape project. The Shanghai Flower Expo, the Renaissance Pavilion, made by bamboo steel. Bamboo, the Rattan Pavilion, it's a landscape installation. Actually, this is very interesting. We're using bamboo steel in Hangzhou City along the West Lake. We used to be plastic and cast iron to make fence, the urban fence. But now we are just using bamboo steel. And also the bamboo steel fence along the Nanji Island Expressway, replacing the iron steel fence. This one is for Taihu Park. It's a scenic spot. You can see the fence, the broad walk, and a small pavilion. Already used for a decade. A very typical interior setting for Wuxi Grand Theater as interior deco material. This one is in Xixi Wetland Park in Hangzhou. This is the gate used using bamboo steel. It's a gateway. It's been built for a decade. It is still intact. Future home in Holland. Bamboo steel window panes, window frame. And this one, Niu Beishan Youth Hostel by a very famous architect. They're using dilapidated old village buildings. They sort of retrofitted the dilapidated buildings and using the strength and the malleability of bamboo steel. And fourthly, I want to talk about the international communication and the prospect of a high-performance bamboo screenber and future development outlook. So basically in 2016, we began to work with the Netherlands, the Southern University of Holland, and we began to have cooperation using bamboo steel. And also we worked closely with the British Architectural Research Institute professor. We have a lot of cooperation with them. We also launched small installations. This picture was bamboo science and technology cooperation between China and Brazil. Minister of Science and Technology signed an MOU with the Ministry of Science and Technology of Brazil. And also some Brazilian companies and businessmen and ministry officials visited Chinese companies to understand. You can see this is the bamboo steel raw material already fluffed. And also we applied for an MOST funding program between China and Brazil. Under this project funding, we visited Brazil and we talked to the local bamboo industry association and producers association. And in the future, we know that bamboo steel, generally speaking, has a good carbon sequestration prospect. And by using our overall estimation, it is a negative carbon product. For every ton of carbon steel, it contains, because it has sequestrated 348 kilograms of carbon per ton of bamboo steel. So it is a very typical negative carbon product. And also when we are manufacturing this, the carbon emission is 1/5 of steel. Per ton of steel emission is 1.49 tons, but only 0.3 tons for bamboo steel. So it's a very typical low emission product. And also in future, when we are mitigating climate change, protecting environment, we may need to change the current status quo of the construction material sector to provide really low carbon solutions, reduce the implicit or embedded carbon, and reduce building emission. Between 2021 to 2025, China will achieve the 5 million square meters of ultra-low emission demonstration building projects. So we have a huge market potential for bamboo structure and timber structure, which is really good news for bamboo steel. Okay, so I have finished my presentation on bamboo screenbar, high performance bamboo screenbar. I'm so happy that I was able to introduce this aspect to you. Thank you very much. So I finished my presentation. Thank you. So just one question for you. Just now you said we have multiple advantages of bamboo screenbar, but in the engineering setting, did you actually encounter any issues or key bottlenecks or technology bottlenecks which are not resolved yet? Some bottlenecks, technology barriers? I mean, in the engineering setting, I'm not talking about the laboratory setting. Yes, that is a very good question. To be honest, it has been developed for less than 20 years. It is actually a very new, emerging building material. So here, I think there are a few issues we need to straighten out, and we need to figure out ways to deal with them. The first thing is the manufacturing process. It has to be automatic and continuous. So currently, for every assembly line, the production function is very small. It's only 5,000 cubic meters, but for the timber sector, one line can produce several 100,000 cubic meters daily. So we really need to develop top-notch machineries, make it automatic and continuous. So the production capacity just too small. So this time in the 14th five-year plan project of MOST, we have listed this as a key technology target. Second thing is that it's anti-mildew effect. Currently, we can have tier 2, grade 2 anti-mildew level, but it's still organic. If you use it outside, sometimes there are mildew. It's natural, but customers don't like it, right? People don't want it to, when it has mildew, it will turn black. So our thinking is that we can increase the mildew performance and also educate our people that when our product is being used, you need to maintain it. And especially if you use it as interior decor, anti-mildew, especially in southern part of China, it's going to be an issue. We need a good solution. Currently, some anti-mildew lab test is testing only one link. It's not really touching from the whole supply chain, from production to delivery to consumption to maintenance. So I think in the future, the anti-mildew solutions need to cover the whole life cycle. And finally, I think we need to educate the architects. Some designers and architects, they don't really know about this material. They think bamboo steel is what it is, but bamboo steel has a lot of applications. It can be used indoor and outdoor, for deco only and for structural purposes. In outside setting, we don't need to have a lot of, for outdoor use, we may need to have a higher structural density, like 1.2, but in stores, we only need 0.9 density. I think we will continue to work with INBAR in future. And in fact, bamboo steel can accommodate your needs. Don't use outdoor bamboo steel for structural use. For interior structural use, you don't need to have a very high density. And our phenolic resin will be even less. The density will be 0.9 instead of 1.2. It's cheaper, it is more effective. And for the outdoor scenario, the 1.2 density is too thick, too dense, difficult to sew, which means that this is a really good material. It's just the designers and architects don't fully understand the properties of this product. The bamboo steel product is just like turning iron ore into iron. When you make iron, you have a low grade, right? Rebar, the lowest grade. When you put in some nickel, it's stainless steel. You add other alloy, you make alloy steel, and it can cost you several 100,000 yuan per ton. bamboo steel is the same. I can make it really cheap, 4,000 yuan per cubic meter. It can also be several dozen thousand yuan per cubic meters. So we can control the strength and the properties depending on your need, and the specifications and the dimensions can be changed according to your need, can be customized, and the structure can be designed for your purpose. Okay, that's all from me. Thank you, Mr. Yu. I think we have another question from a foreign guest. From the cost point of view, screenbar and cross-laminated bamboo, is there a big price gap if you use it in the building sector? If it is too expensive, then it will encounter multiple issues. I think that is a very good research topic even. I'm actually talking to another company. We are working on the so-called directional bamboo screenbar. And it can be a hybrid even. Bamboo steel is around 0.2, 1.2 density level. Bamboo, laminated bamboo is between 0.6 to 0.8. So the two materials cover a full spectrum depending on the density. Bamboo steel's mechanical property is better than laminated bamboo. The laminated bamboo steel is around 0.7 density, very similar to the hard broad-leaved timber. So bamboo, laminated bamboo can be used in a suitable scenario.
For example, now we can use this as the heavy-duty trucks floor, and 9,000 RMB yuan per cubic meters. So if we want to use bamboo screenbar, we should give full play of its mechanical strength, because it has durability advantage comparing to average timbers. We can improve the structure as well. So I'm not talking about the bamboo screenbar is better than other timber resources. It's just suitability of different types of structure. There's a second question. And this question is asked who would be the contact person if they want to do some investment in the project for the international cooperation. Can you leave some contact information? Yes, I will leave Professor Yu's contact information in the chat box. And we look forward to your investment in China's bamboo industry.
Thank you all. I think your study is really interesting, it's meaningful. Work on the biomass, strength and properties, and its hybrid use with reinforced concrete. But I want to know that you're adding like a fresh bamboo fiber. I'm wondering, is it possible to use waste like a bamboo sawdust or I mean, end of life furniture, because they're waste anyway, you turn them into fiber and you are disposing of waste furniture. Do you have any like a specification for the processing of the feedstock? Do you really need fresh bamboo to turn into fiber? It's a very good question. Previously, we did some testing. We were using fresh fiber. We just blow them, steam them, dry them, turn them into fibrous stuff. You're talking about the wasteful furniture. I think no problem. But if they have plastic, if they have glue, then it could be problematic. Or raw feedstock will be no problem. Yeah, like bamboo chopsticks, right? You can use that because they don't have glue. Yeah, that is a very good idea. I also have a question for you. I mean, previously we did some similar study adding fiber into the concrete. Superficially, it is fiber, but it's not extracted fiber. It is like small sticks. It's not in the fiber state. It's like small chips, stripes. So your fiber, is it really like a fibrous property or just a small stick, thin stick? No, it's not a stick. I don't know how to call it. It's not like a thin chopstick like stick. We are using high temperature steam to blow dry it. And then you get really fibrous stuff. Yeah, it's like a Mr. Xu Bing's feedstock. We have developed a machine to steam blow, but the processing capacity, throughput capacity is still too small. The fiber has to be small in order to have the highest per unit strength. We were pulling over to 700, right? It is still having strength. If it is small stick, it cannot reach 700 tensile, because you have to remove all the vascular wall. And what about the concrete? Do you have a concentrates or aggregates? I mean, the fiber is too soft. We are using stick. It's difficult to, stir them evenly. I mean, how do you mix them evenly? The fibers too, it moves around. I can tell you, when I was stirring them, sometimes, the fiber, they just move to one place. Sometimes the fiber will break. During stirring, we didn't really try to control. We just make sure that it's as evenly distributed as possible. Then that is the maximum we can do, because when you put it in the concrete, sometimes it breaks. But for the fiber, the longest length is around 30 millimeters. So it wouldn't break too much, because once it is very thin compared with stick, it won't break. It has some elasticity or resilience. Yeah, sometimes it floats. You cannot penetrate the depth of the concrete because it's too light. It will float on the top. And also, if you're mixing up with the raw aggregate, but for us, it's lightweight aggregate. The aggregate itself is light. So no problem. No problem for us. Okay, great. Great. Thank you for your question. Yeah, we have a question in the chat box. basically the species of the bamboo, are there any like preferred species? We are just using Mosul bamboo. We didn't really try to figure out the specifications of the fiber. I think all fibers, if they reach this level of thickness, they have a very high strength. It's just like a steel. Mr. Yu talks about all types species in the bamboo steel. We are using, the lowest grade Mosul. You remember that ladder at the bottom? We just use it. It's so abundant. We don't really think it matters. Once it is really fibrous, it's really thin, I think it already meets the needs. I think all species would work. I don't really have any preference. Thank you for your answer. Thank you very much.
Hi, sir. Am I audible? Can you hear me, sir? Can you hear me? I'll share my screen. Okay. Okay, for a while. Am I loud and clear? Can you see my screen, sir? Okay. Okay. So before I start my presentation, I would like to thank the INBAR. This opportunity is so great, and I am very thankful that I was chosen one of the presenters. Okay, so good evening, ladies and gentlemen. I'll be giving the results of my study in bamboo shading reinforced concrete wall panels. I have done this research way back, so I might be a quite I mean, I'm quite in terms of advancement, so compared to other speakers. Okay, so let me start with the introduction. This study utilized wood waste as an alternative raw material for structural components of houses, and this is one of the most promising waste management process to solve both the problems of disposing of wood waste and house construction backlog. Because here in the Philippines, we have a lot of things that we are looking in the low cost housing, because many of our community here needs low cost housing, especially that the pandemic has been spreading last 2 years ago. Okay, now bamboo shavings as wood waste. Bamboo shavings as wood waste produced from agro industries that manufacture hand. Yeah. Yes. Okay, so I'll try.
How about that? Is it louder now? Hello? Okay, so I think I am clear now, right? Okay, okay, thank you. So let me continue. As I was saying, bamboo shavings as wood waste produced from agro-industry that manufacture handicrafts, furnitures, artworks are usually burned or dumped in the field. Recycling of such waste can help to reduce both the waste disposal and housing is shortage problems. So we have here especially in our province in Pampanga, Philippines, um, they use bamboo for agro industry, like they are doing some nipa hats, the one that are bought from different industries here in the Philippines, and some of these nipa hats are locals housing. So the wood waste from this manufacturer or agro industry manufacturers are used for this study. So these are wood waste, okay? So I use wood waste as my fiber. Okay, in the next slide is the significance of the study. So this research study looked into the possibility of utilizing bamboo shavings as secondary reinforcement to develop a locus wall panel. Later, I will show the picture of this wall panel. So the developed bamboo shaving reinforced wall panel can be generally applied for non-load bearing wall construction and mainly for small scale housing. So it's very essential that we use lightweight, low-cost materials for some of the community houses. So for low-income people or Filipino people, the result would contribute to the concrete and construction industries in developing an alternative material for reinforcement that is both, of course, cheap and locally available, since the materials are from wood waste of agro industries. And one of the results or one of the significant results of the study is to determine the mechanical properties in terms of concrete strength and flexural strength of bamboo shaving reinforced concrete. So this is notated as BSRC, or that is bamboo shaving reinforced concrete, having ratio of 2% for the first treatment, 3% for the second, and then 4% for the third treatment. And T4 would be the concrete control, okay, without the fiber. Okay, next is, by the way, the mixture is by weight. So next is this compressive strength graph. Shows in this figure, figure 1 to 3, the comparison of the mean value compressive strength of concrete cylinders at 7, 14, and 28 days. So as you can see in the figure, that the T1, which is the 2% bamboo with 2% bamboo shaving by weight, T2 is the 3% bamboo shaving by weight, with the 3% bamboo shaving. And then T3 is with the 4%, and lastly, the control without the fiber, bamboo fiber on it. Okay, so we can see here in the seventh day, the highest would be the first treatment, and also with the 14th day, the T1 also has the highest with fibers, of course, and in the 28 days, it shows that the T2 has the highest compressive strength, but all of those would not supersede the control. Okay, so as you have seen the figure a while ago, it shows that T1 has the higher mean value than T2 and T3. However, their value is always lower than the control, that is T4. It can be observed that as the volume of the shadings increases, the compressive strength of the composite decreases. So it was further observed that the compressive strength of all this treatment with bamboo shavings decreases with age. And the possible explanation is that the composition of bamboo shavings. So I would like to clarify that the bamboo shaving or the bamboo shavings from agro industry did not have any treatment. Okay, so it doesn't have any pre-treatment before it is mixed to the concrete. So what I did is just the bamboo shavings were cut into about 1 millimeter to 3 millimeter thickness, with a length of about 3/4 inch to 1 inch. So without any preservation or any treatment, it is mixed to the concrete with the ratio of 1:2:4. That is for the cement, sand, and gravel. Okay, next is the result of the comparison of the mean value of flexural strength of the concrete cylinders at 7, 14, and 28 days. So as you can see in the figure, on the 7th day for curing treatment, the flexural strength shows that the T2 has the highest flexural strength, while for the 14 days, T3 supersedes T2, and then on the 28 days, they have almost the same or no significance between T1, T2, and T3. Okay, so in the figures 4 to 6, which shows the flexural strength of the concrete beams at 7 days, 14 days, and 28 days, respectively, the result shows that the flexural strength of all of the treatment, T1, T2, and T3, are all above the control. T4 for 7 days and 14 days, and above equal at 28 days. The recorded data reveals that with the inclusion of bamboo shavings as reinforcement, to a certain extent, it will not anymore increase the flexural strength of the hardened concrete mixture. Furthermore, the flexural strength of the concrete mixture with bamboo shavings decreases during 28 days curing period. The probable reason to this is that the bamboo shavings would have been deteriorating since these are organic materials. Again, I would like to clarify that there is no treatment on the bamboo shavings that was used in the study. Okay, now this figure 7 shows the prototype of the bamboo shavings reinforced concrete wall panel. So these are like the one that we use for the NLEX or the National North Luzon Expressway of our country. Okay, this is the one of the biggest route highway or expressway in the Philippines. So this BSRC wall panel are used for walls for fences, okay, along the way. Now, it is non-load bearing, of course. And considering both compressive and flexural strength that was presented a while ago, the best formulated bamboo shaving reinforced concrete mixture is the one with 3% bamboo shavings. Thus, it was developed in a BSRC wall panel with dimensions 50 millimeter by 600 millimeter by 1,200 millimeter, or that is also 2 inches by 2 feet by 4 feet. So the constructed non-load bearing BSRC wall panel from the best formulated mixture was evaluated in terms of aesthetic and cost effectiveness. So there are survey questions that were floated for different fields, like the civil engineering field here in the Philippines, some of the skilled workers, laborers, and some of the architects. So these questions were given to them, and then they gave their answer. So the results shows the following. So considering both compressive and flexural strength, it turns out that the best formulated bamboo shaving reinforced concrete is one with 3% weight 3% weight percentage of bamboo shavings. Thus, it was developed into a BSRC wall panel to evaluate its cost effectiveness. The study also shows that the inclusion of bamboo shavings of concrete matrices will not increase both its compression and flexural strength. However, the test result shows that the compressive and flexural strengths of the specimen are both in the standard strength required for non-load bearing components. So it can be used for different ranges of utility. Like these developed BSRC wall panels are suitable for a lot of applications, such as materials or components of fences, partition walls, bearing wall, road barriers, retaining walls, noise barriers, channels or spillways, and other non-load bearing structure. So also the wall panels can be easily handled and installed by a team of 2 men. Moreover, the developed BSRC wall panel is cheaper, and it is cheaper in cost compared to the commercially available wall panels. And another findings is that the inclusion of 3% bamboo shavings lowers the cost of the wall panel to more than 50% compared to that of the commercially available wall panel. As described, all necessary resources are available locally at low cost and has a low energy requirement, because we have used, or I have used a wood waste, okay, or bamboo shavings from agro industry. So it's just a waste that you can be dumped anywhere, but I have collected them to put it on a concrete, in a mixture of concrete. Through it may be more, though or rather, it may be more difficult to acquire the mold in a small town. The mold can be manufactured in welding shop for locally and is relatively cheap. I'm speaking of the mold for the wall panel. Okay, and that would be all. Thank you so much. Thank you. Sir, can I share again? I did not have a picture of my presentation. And okay, yeah. Uh, okay. Ma'am, this is my research for my master's degree. Okay. Yeah. Yes, ma'am. Yes, ma'am. But this one is not patent yet, and I did not. I mean, I presented it here in the Philippines. This is the first time I presented it in national level, and I think, yeah. My comparison is the one that is being bought in the market. So I compared a commercially available wall panel to my product, to my product. Thank you. Okay. Yes, sir. Yes, sir. I'm looking at it, and I think there is a question here. Okay, so how big is the local industry and their capacity to make BSRC in black panels that can be used in more use cases? So the for I think the one that I have compared with my study, the commercially available one is used for the national road as fence or barriers for the which is parallel to the national, I mean the North Luzon Expressway. So it's a quite big industry, and I was also invited to explain to them because this wall panel that they are using, they use literal horizontal bars, but mine, I did not use horizontal bars, so I just use secondary reinforced, and that is bamboo fibers. Okay, so they are saying that they might use my study because some of these steel bars that they put on the national road, they are being, I mean, the people, they took those reinforcing bars and they sell them. So the fence are being damaged because of that. Okay, I think another question here. What are the water-related properties of these reinforced products? Okay, so honestly speaking, I did not do any submerging or test or what do you call that? Water absorption test. I haven't done that, but in my during my curing period, I can see that this mixture is very porous. And water can pass through it because some of the bubbles are escaping from the outer surface. And honestly speaking, there are some honeycombs. Okay, so because of I think the fibers are they are crumpled when you mix them with concrete, and so some were not distributed very well. I hope I have answered the questions. Okay, so another questions are here. How can my team get in touch with your local industries? Is there any website of all the companies, organization, farming groups? Okay, I think I'll just give my email address, and then I can search for you, so I can send some of their um, their websites and contact information. Thank you.
So we used a different density, 1.1, 1.0, 1.25. That should be, are you using different glues? We actually have some, you can choose the Chinese channel if you want. Or what kind of glue you are using? I also have a question for you. Just now you have made a very interesting presentation. I just want to know that SAF, for the aging and the creepage, do you couple them in the study? Do you have a coupled study? I mean, a lot of things, when they're under load, they age and they may have creepage, right? When you put them under load, they're also exposed to the sunlight radiation. Did you do any coupled study at CF? We did. But the thing is, we do them separately. We do aging tests, right? And outdoor aging and artificially accelerated aging. And for creepage, we have artificial creepage. Whether they're coupled, I think we just later do a statistical study. We try to figure out if they're actually coupled. If they have a nexus point, we may try to find the coupling effect. We don't really do both at the same time. Currently, we separately study them. Okay, I understand. Maybe a small question. So for the accelerated aging, accelerated creepage, we will convert that into ordinary conditions, ordinary work conditions, reference temperature and conditions. And for the accelerated aging, is that qualitative explanation? How do you explain the quantitative data? You convert them into ordinary conditions? Actually, in our study, I talked about under natural conditions. I used two natural aging scenarios. One is humid and hot in summer part of China, in the southern part of China. Another one is dry and cold in northern part of China. So I sort of chose two extreme natural conditions, which means that I use the accelerated aging to simulate outdoor long-term aging effect. So I have chosen an extreme condition, 63 degrees Celsius, using fresh water and seawater for 14 days and 28 days. And I set up a model. I tried to compare the figures in the lab and outdoor aging data. I think I have done artificial accelerated aging up to 6 months to simulate aging for 10 to 20 years. I try to fit the curves and for different bamboo species and for different density level, I try to forecast the aging and the degradation behavior for an outdoor scenario. I want to use accelerated aging to understand a number. So in future, I don't really need to do an actual natural aging. That is the purpose of my study. So the purpose is to build an aging model, right? You try to find the quantitative conversion between artificial aging and natural aging. Okay, thank you. So in the chat box, we have a question from Jim. Actually, the seawater tests was in the laboratory, and we're using the seawater simulation in the laboratory. Thank you. It's not in outdoor, it's in the laboratory. Thank you.
Yes, good evening. Can you hear me? Well, it's evening already in the Philippines. I don't know about the time zone in the other countries. Maybe it's morning or afternoon. But anyway, thanks for having me here at this Global Bamboo Interton Congress. I'm happy to share my one of my research to this conference. So for a moment, I would be sharing my presentation. Can you see now the screen of my paper? Okay. Okay. The title of my paper is Development of Arc Laminated Bamboo from Thermally Modified Segments. I'm from the Department of Science and Technology, and my agency is Forest Products Research and Development Institute. Okay, so for the introduction, so we all know that bamboo is a very versatile material. It is fast-growing, non-timber forest products, and it's traditionally used for furniture, handicrafts, and light structures. But in modern times, like what we have now, especially in your country, in China, technological advances have made possible the use of bamboo in architecture and construction of medium-rise building. But in the case of our country here in the Philippines, we're just about starting, the government exerting effort to develop bamboo industry in our country. Okay, in our country, actually, we are laminating bamboo in just 2 ways. Unlike in your country, you already have bamboo screamer or bamboo steel. We are laminating bamboo in 2 ways. One is horizontal lamination and vertical lamination. These two processes actually are not so efficient because here in the Philippines, we're utilizing mostly the bottom part of the bamboo up to somewhere in the middle part, or about 2/3 of the pole. And 1/3 of it are actually put in other use because it's not economical anymore to recover a rectangular slot on the top portion of bamboo. So what we did is we developed another method of lamination, and we call it laminating the arc the laminating bamboo in its natural arc. So as you can see in the photo on the right, this is a cross section of what we did in the top portion of bamboo. So we split it quarterly, and then we get arc of uniform dimensions. We actually sorted them based on their arc, and then we laminated those arc to form this figure that you saw in here in the right. Okay, as a lignocellulosic material, we know that bamboo is very susceptible to dimensional movement and biodeterioration. In the Philippines, we are a tropical country, and there are so many biodegrading agents that could actually easily deteriorate bamboo. And one of them is are the insects that is most bamboo is most susceptible to powder post beetle. And another thing is the problem with the lamination is that we are a tropical country, so we experience cyclic changes, extreme cyclic changes in temperature and during summer and then during rain season. So bamboo lamination is actually prone to delamination of the glue line, especially if you're just using an ordinary adhesive like PBAC. So if it gets submerged in water, let's say for 24 hours, it would probably delaminate, unlike other adhesive. So I would like to introduce this technology. Actually, it's not relatively new anymore because it has been around for about a decade or two, I guess. So this is called the thermal modification technology. It is a non-hazardous approach to protect the bamboo by exposing it to high temperature using various media. This involves a high air with a hot air with steam or hot air in a nitrogen atmosphere or hot by immersion of a lignocellulosic material in oil. So you can see in this photo some of the bamboo poles that we modified. The leftmost photo here is the control or the untreated, and this two is the one treated with under steam, and this one is under oil, the relatively black one. So as I mentioned earlier, since rectangular slot lamination is not efficient to utilize the bamboo's whole length, so we introduce the lamination of arc-shaped bamboo segments. So it's one approach to laminate bamboo and to fully utilize the whole length of the cone. So this study investigated thermal modification and arc lamination of bamboo. So we basically combine two technologies here. So we seek to produce a biologically durable and dimensionally stable engineered bamboo laminate with a potential application in the construction industry. So shown in these photos are some of the activities that we did in the experiment. So after we obtained the bamboo poles from the forest, so we air dried them, and then for about 2 months of air drying, so it attained the equilibrium moisture content. So we process it, we cut it to length, we split it, and we put it first in the modification chamber, the one with the bio steam and another one's bio oil, and we use temperature of 175 degrees Celsius and 200 degrees Celsius for about 30 minutes. So after treatment and after conditioning the sample, so we quarter split them, and then we remove the nodes, and then the method that we use to Rattan the outer peripheral zone and the inner peripheral zone, or the cuten side and the inner side of the bamboo, is just by sanding. So after removal of the nodes, it was sanded manually and then sorted and graded according to their arc, and then we laminated and using PUR glue or polyurethane. It's a one-component adhesive. And then we press it using a pneumatic press, and then for a specific pressure about 1 megapascal. And then after it, so we condition the sample and prepare it for testing. So we cut the sample according to ASTM standards, but with slight modification in the sizes of the specimens. So these are the samples here. And so we tested the physical properties and the mechanical properties and decay resistance. So under the physical properties, we get the relative density, the thickness swelling and water absorption. For the mechanical properties, we tested the samples two ways. One is loading by the tangential loading, and another is radial loading. And we also test the durability of the samples against decay. So the key findings and results here are, first is the color change. Color change may be an advantage because if you have thermally modified bamboo, you don't need to stain anymore or to color the bamboo to attain a brownish color, because it's naturally after the treatment, it's brown compared to the untreated ones. But it would be a disadvantage for those who wants natural color of bamboo, like the yellowish color. So it depends on the end use of the bamboo and the user. So for the physical properties, you can see here that for the treatment, we have here the untreated or the control, the steam, and the oil. You can see here the moisture content of the samples. For the untreated ones, it's about 12.27%. With treatment, the equilibrium moisture content actually got lowered. So it's about 7.58. For oil, it's 7.1. So basically, there's no difference between the steam and the oil. But for the relative density, the untreated ones has about 0.74. With treatment or thermal modification, the relative density reduced a bit, but it's a bit, but actually there's a significant reduction. For the thickness swelling, you can see here that the untreated ones has about 3.05% thickness swelling, but with the treatment at 175, there is a reduction in the thickness swelling. So the same thing with the water absorption. There is less, the material absorbs less water. So it's a proof of improving dimensional stability of the material. Now, for the resistance against decay fungi, so we tested the samples against two kinds of fungi, the brown rot fungus and the white rot fungus. So this is the Lenzitis striata and the Pycnoporus sanguineus. So you can see here from the table that the treated ones, or the steam treated and the oil treated, actually improve the resistance from being moderately resistant to highly resistant. The same with the Lenzitis striata. So on the figure at right, you can see the photos, control, steam treated, the oil treated, and you can see the Lenzitis striata here on the right, and then here in the Pycnoporus sanguineus. For the mechanical properties under the flexural and compression strength, the results show that between the untreated, the steam, and the oil treated, the MOR, or the modulus of rupture, was significantly reduced for the tangential loading. But for the radial loading, there seemed to be no significant at all. So we accounted this for the degradation of some components of the bamboo, like the hemicelluloses, specifically the hemicelluloses. Now, for the modulus of elasticity between the radial and tangential, there's statistics shows, or the results show, that there seems to be no difference at all between the untreated ones and the thermally treated ones, both in oil and steam. For the compression strength, and same thing, there's no significant difference between the control and the thermally treated ones. So except for MOR, that's the only one, the only mechanical strength properties affected, all others are, there's no significance at all. Now for the shear strength, or the band shear strength, to test the strength of the glue line between the untreated, steam, and oil treated, the blue bar here is the dry shear strength, and the green one here, the green bar, is the wet shear strength. You can see here that although there's slight reduction for the steam, for the oil, they're almost similar. Statistics showed that there's no significant at all between the bond shear strength of the untreated ones and those treated with steam and oil. And one thing here is that the shear strength of the both untreated and the thermally modified samples actually did not surpass the 1 megapascal strength. So that means you have to consider the cohesive wood or cohesive bamboo failure for it to pass a certain standard. So under the strength of 0.6 to 1 megapascal under the Philippine adopted standard, which is patterned after ISO, there should be at least 40% cohesive bamboo failure. But unfortunately, both the untreated, the steam, and the oil did not surpass that minimum requirement of 40% of failure. And we accounted it to there is still some presence of waxy layer on the outer zone and then the peripheral zone of the bamboo. So we are recommending that maybe other methods of scraping out, or maybe mechanized scraping of the cutin layer and then the innermost layer, would probably improve the bond shear strength of the arc laminated bamboo. So now for the conclusions, we can say that bamboo thermally modified in oil or steam environment at 175 degrees C for 30 minutes, at least it gives better bamboo segment properties than the control or untreated bamboo. Now, orientation of loading during static bending test influenced the strength properties of the bamboo arc laminates. And in general, lamination of thermally modified arc bamboo segments is feasible, with resulting laminates showing improved dimensional stability, decay resistance, and little or no effect on strength properties except the MOR. Okay, that's the end of my slide. I would like to acknowledge the funding agency, the UST Picard, for funding this study under the project titled Gluing and Finishing Characteristics of Thermally Modified Bamboo. That is all. Thank you. Yeah, thank you for that question. I failed to mention it. Actually, in the experiment, we utilize spent cooking oil. So these spent cooking oil are actually in the Philippines. These are collected from fast foods and restaurants, and there are accredited holder or treater of this spent cooking oil. So they treated it, and then that's actually the one we use, because if you would use fresh oil, considering the bath that we use, that is about 4 feet by 3 feet by 4 feet by 8 feet chamber, so we would have to pour in so much fresh oil. So we use actually spent cooking oil to treat or to use it as another medium for oil heat treatment. Yeah. How big is the industry? How to get in touch with these companies? Actually, there are emerging bamboo industries, micro and medium small scale industries in our country. Actually, they are just we are just starting because we realize that with the government effort to help the curb, the effect of climate change, because we all want to prevent our trees from the forest. So with bamboo, we all know that can grow even after cutting, it can still grow again. So the focus now, one of the main focus in our institute and even our government agencies to boost the bamboo industry. So there are micro and small, micro and medium enterprises involved in bamboo processing here in the Philippines. I think that's the question. How big is the industry? How to get in touch with these companies? maybe how to get in touch, you can actually email me you can give me your email and then I will link you to those industries. Thank you. Is the question already answered? Thank you. Thank you so much.
Thank you, Professor Lee, for your kind introduction. This is a topic of my presentation, Mode 1, translaminar fracture of CLB and layup effects. We all know that bamboo material as a construction material enjoy a lot of advantages like renewable, low carbon emission, prefabricated offsite, and quickly assembled. And the previous study reveal it has excellent seismic performance. In the bamboo structure, you can easily find the splitting and the fracture cracks in bamboo construction. You can see in these pictures. It's due to the structure per se of the bamboo because it has anisotrophy problems. It has a lot of fibers. Actually, fiber is arranged horizontally. Vertically, there's no fiber. As a result, it has an anisotrophy problem and make the bamboo cracking. Our study revealed that the interlaminar fracture property in bamboo is very low. It's between 200 to 400 per square meter. These directions brittle failure. That is once it reached the peak load, then the load would drop dramatically. In order to make the bamboo more suitable for construction, we want to improve the bearing capacity of bamboo and also to reduce the brittle failure. Otherwise, it's very risky. Therefore, we studied the CLB, that is cross-laminated bamboo. It's just like CLT, cross-laminated timber. We glue them together in the two directions like this. Then there are going to be fiber distribution on both directions. In order to make CLB, in order to improve the CLB's property, we need to have an in-depth study on the brittle failure. Because in the construction, our focus is on translaminated fracture. Because this laminated panel is going to be used as the shear walls. So most of the failures are from translaminated fracture. So this is the study focus. We conducted 2 types of study. The first one is TPB, 3-point bending. 2 types of CLB panels being used. Different fiber contents. 4:1, that is the fiber. Horizontal versus vertical. And due to the fiber directional relation, we give them different names. C41 specimen means the vertical fiber versus horizontal is 4:1. And the 3:2 means horizontal versus vertical is the ratio is 3:1. So it's called specimen 3:2. For the different specimen, we produce 2 lengths just to calculate the fracture toughness. This is a TPB device, CMOD, CTOD. In the TPB test, we use a vertical and horizontal test. Then we have a different specimen. You can see CLB of different sizes. Then we had the tensile test with double edge notched tension. This is our testing device. You can see on both sides, there are sensors to make sure the balance is being achieved. And we installed such sensors to make sure the balance in the test. This is the TPB test result. This is after the destruction. You can see the different forms. The specimen 14, specimen 2-3. Of course, you can only see the surface, but you can see the fracture happened following the initial fracture direction. And the C32, C41 also follow the initial fracture direction. But gradually, you can see for this C41, there are obvious horizontal fractures as well, comparing to C32. Likewise, for this C14, this is a TPB load CMOD curve and load displacement curves. Red line means levelized average graph. And when we calculate fracture toughness, we use this red line average curve. This C14 specimen situation. Once reached the top load, peak load, then it dropped sharply. You can see this drop sharply reflects the brittle failure feature. But for this levelized average graph, there's no obvious fracture toughness changes. So there are some errors caused. This graph shows specimen 2-3. Also, after the peak load, there's a sharp drop showing the brittle failure. With additional horizontal fibers added, this specimen 32, the brittle failure is not so obvious. You can see there is a non-linear trend before reaching the peak load. This is a C41 specimen. The brittle failure, if we use a load CMOD curve as an example, it is not so obvious. Then we had very careful observation for each individual specimen, but our observation can only lie with the surface of the specimen, not the inner part. So we can show you the forms after the destruction. This is a transverse crack tip. But if it is the horizontal, like the lower part, then the destruction would be more complicated. So what we are observing is the lower part about the brittle failure, about the cracking forms. From this curve, we can see once the initial crack began, it started along the fiber grain direction. That shows the cracking occurred. And gradually, this cracking is expanded horizontally, following the fiber direction. Actually, this is a cracking of a combination of mode 1 and 2. On this curve, it showed nonlinear feature. With the further expanding of the cracking, then it reached the peak load. Once it's being expanded to a certain degree, the upper level fiber had also breaks. You can see from P3 to P4, the speed was very fast. These are the fiber breakage. This is a mode 1 breakage. Once reached the P5, you can see this fiber breakage. Horizontally, the expansion is no longer obvious. There are fiber breakage situation. For the
end part of the lineal section. And then at P2, you can see on this load, we have nonlinearity. And also here, you have mode 1 and mode 2. One is mode 2. Mode 2 is a shear type breakage. And then later, transversely on the top of the transverse crack, there will be a breakage of the fiber. That is the load point 4. At load point 5, unlike specimen 1, here we still have very clear transverse cracking. You can see this curve is different from specimen 1. in specimen 1, at a maximum load, it will have a cliffside drop. But here, for this specimen, they have a obvious extension of transverse cracking, and you can see the curve is less steep than the previous curve. So here we can see that this is the point 6, and then you can see we begin to see clear fiber breakage. So transverse crack extension is a transitional period. So it can actually keep the specimen intact instead of brittle damage. A lot of studies of the hybrid composite products had this similar observation. And since we had a very complicated breakage, we have mode 1 and the mode 2 breakage, we don't have a theory to calculate the breakage elasticity. So we understand even for composite materials, we don't have enough literature, so we don't have a good formula to calculate. We can only look into some correction to do our study. And here we are using 3 ways to calculate the R curves. First, we're using 2 types of specimens. We have the load curves. We calculate the delta area between the 2 curves. The method 2, we are using the omni-homogeneous property to calculate the R curve. And we looked into the damage at the maximum load point, and we corrected the formula. This is the corrected formula. And method 3 is the area method. It's just the delta area under the load curves. So we use the 3 methods to calculate our curves. None of them can accurately represent the real-life specimen, the also cross-laminated bamboo materials, a breaking curve. But interestingly, the R curves are fitting. The trend and the values appears to be fitting with the minimum error. You can see for the 3 modes, for 3 methods, the curves are showing the similar trend with a good fitness. And for the specimen 2, method 1 may deviate at the tail side. Maybe when we are measuring the displacement of load point, there could be some error. And also we feel that for specimen 2 situation, method 2 appears to be more accurate. But in any case, we feel that all 3 methods work, and the margin of error is acceptable. And the C41 specimen, they had really good fitting in the first part, but later all 3 methods deviated drastically from the main trend curve. This is for C41 specimen. At the load point, there was a deformation due to compressive load, which means that the measurement of the load point displacement is inaccurate. So the tail of the curves began to deviate drastically. And also now we are using the traction separation relation obtained from the R curves. It's a constitutive model. And this will have a correlation with the tensile load testing results. Now we can look at the direct tensile test. This is the failure patterns. Apart from a few specimens which were broken at the two ends, most failed through the initial fissure. You can see similar, they break around the pre-incision line. But C32, it had some other damages. The C32, it has a larger fiber density, so it will demonstrate other breakage pattern. The fibers are broken, and along the fiber, we also have cracking, and here also breaking of the fiber. And here we have some cracks parallel to the grain, fiber grain. This is the cross section after fracture. You can see this is specimen 1-4. The fiber has broken. The fiber has detached. It's like a fiber pullout. Fiber pullout is quite rare. And here you can see we have more fiber pullout and less fiber breakage. C32, we have mostly fiber pullout, very little fiber breakage. So this one is the comparison between TBB and tensile test results. This is the tensile. Maximum tensile stress, it is fitting. The difference between the average curve and the curve of single specimen, especially at descending part after the peak load. The red curve is the TPB curve, and the black is the tensile tests. So the curve at the maximum stress point, it has a very shallow curve. But for the tensile, there is a sudden breakage. So there's a big difference. We have the analytical results. Maybe data processing had some errors. We are using the average curve to calculate the breakage resilience. The average curve could deviate from real-life measurement curve, and also the calculation method may be flawed. Control your time, please. And also the rigidity of the tensile, and also we are comparing the cross-laminated and non-ortho cross-laminated. The rigidity of the cross-laminated bamboo is higher. And also here, the tensile strength and initial fracture toughness basically increase linearly with the transverse fiber percentage. An increasing trend of critical fracture toughness is greater than that of the transverse fiber percentage. And you can basically the transverse and the longitudinal arrangement of fibers in CLB significantly improves the fracture toughness and energy consumption, especially the critical fracture toughness. And with the increase in fiber content, the failure mode changes from fiber prickage to fiber pullout, which can improve brittle failure characteristics. And larger fiber content in one direction will cause greater aneostrophy in CLB, which will cause failure in the relatively weak direction. So maybe one question from me. For the tensile load, there was a cliffside-like drop. And you said for the TPB, they had an average data number. And maybe for the tensile side, the specimen dimension, when you are doing tensile study, all of them dropped immediately. There wasn't any mechanical recovery because it's because of the dimension of that specimen. Because you had two big incisions in the middle. That is possible. Maybe it is something to do with the form and dimension of the specimen. So we didn't really had a fully fledged testing methodology for all the specimen. We didn't really look into the thickness of the incision in the middle. And for direct tensile, it has a high requirements of the testing rig. So maybe it's just because the dimension is too small, it shows a sudden drop of tensile resilience. Okay, thank you very much.
Can the secretariat help with the screen sharing? One moment, please. Kevei will do so. Please give me one moment. Sorry, we want to make it full screen. One moment. Can you see my shared screen?
We are doing a very small specimen test for sound isolation. We only just test is sound isolation tests. Later, we will do mechanical tests to see if they were actually full of, especially anti-pullout and anti-shear data. I can leave my mailbox, and if you have questions, just send to me. Okay. Thank you. So you said that for the snail, if your nail is larger in form and diameter, it will have a better isolation. So you only considered bamboo screen bowl. Are you using it in the cross-laminated bamboo? Or are you using full screen bowl screen to isolate sound? And then it would be more convincing. It's just a small test. I just want to see whether it will have a good sound isolation effect. The screen bowl, of course, has a higher mass, higher density. Definitely, it is more effective in isolating sound. So maybe in future, you can do more comparative study. The current convincing power of the study is weaker because you don't have a comparative study. It's just my suggestion. You can go for additional study in the future. Thank you. Yes, I will continue to optimize my study. So good day, everyone. I feel very happy to attend today's presentation. My topic is study of dragon bamboo and eucalyptus wood for cross-laminated timber fabrication. So I will talk about the research background. We know that the bamboo and the timber, they are non-homogeneous products grown naturally. They have a lot of mechanical similarities. And since bamboo has good mechanical strength, then people are using composite material. Currently, we have a glulam, orthogonal glulam model with eucalyptus wood, and we try to study the different tensile and vertical strengths at different kPa. Your screen is different. You're like in the projector screen. Yeah, you need to change the presentation mode. Okay, let me adjust. So I will, my study is to using the timber to replace, using bamboo to replace timber and promote the development of rural areas in Yunnan province to see if we can use bamboo to replace Eucalyptus grandis. And we use the bamboo with Eucalyptus grandis in an orthogonal glulam model. And so its strength will meet the national orthogonal glulam standard. So I'm using Europhili E. grandis. It comes from Yunnan forest farm. And also we have Dendrocalamus giganteus, also harvested from Dehong County. We are using phenolic formaldehyde resin, phenol plus formaldehyde. And we mix them together into a glue. And we have the PMDI. It is a 1-to-1 mass mixture. PMDI is applied by Wanhua Chemistry Co. Limited. So we have several variables. We have with or without the green outer wall layer of the bamboo. And also in the control group, we have eucalyptus wood. So actually our mixture is 120 grams per square meters. That is the application amount of the glue. I also have 2 types of glue, PF or PF plus PMDI. So when we manufacture orthogonal glulam material, we need to meet national standard for strength. I have done the following testing. We feel that the cross-laminated timber plus Dendrocalamus giganteus can meet the national strength in all areas. It has a very strong tensile strength. And actually, when you keep the outer greenish wall shell of the bamboo, you can actually give it higher tensile strength. From the results, it means that when I'm making the glulam model and the TPB bending point model with a higher tensile strength and bending strength, then when you keep the green outer wall of the bamboo, it has the highest 3-point bending strength. And eucalyptus as the surface layer control group, it has the lowest strength. So I have done some numerical study and statistical study. We feel that for the tangent side, it has a good drying properties. And the perpendicular, it has less strength. This is the schematic diagram of the billet mode and the model master view and the orthoglulam model. This kind of product has a very good dimension property. According to some study, with the low molecular weight PF plus PMDI as a hybrid glue, maybe is the best gluing agent between timber and the bamboo. When we use the PF between the 2 materials, the expected result did not show. When we keep the green outer wall of the bamboo, it doesn't really have the highest strength. Those with removed the green outer shell actually is stronger, which means that when we use pure PF as a glue agent, simply does not meet our test expectations. When I'm using PF plus PMDI, the existence of the green outer shell increased 52.7% of tensile strength, which is higher than the grade 1 strength in the national standard, and also higher than the bending strength in the E1 level in the national GB standard. For the mode of fracture and the failure, the first one is the PF plus PMDI glue. It has a rolling shear failure. And also the second one is the pure PF glued layers, the interlaminar shell failure. The final one is the control group, the eucalyptus wood PF laminated material. So you can see at the bottom, there's a clear damage by tensile load. And when I change to the bamboo, we don't really have a tension damage. And also for the rolling shear failure appears greater with the PF, but delamination dropped much more when we have PF, PMDI lamination. So when we use the hybrid glue, the pure PF lamination without a green wall is higher than the PF with the green wall. So we want to see why there's a gap in order to figure out which would be the best resin glue, PF or PF with PMDI. We can make some comparative study. So I bought some CLT panels available in the market. I try to put them with the PF and PM plus PDMI. You can see that PMDI and PF, they have basically the same level of adhesiveness. And when you can mix them together, they actually have a higher solidification ability so that it will increase the bending strength of laminated bamboo with the green shell. And also you can see the failure appears at the 8 and 9 position. Then if they can penetrate to these two layers, it will have the best binding power. Under my fluorescent microscope, you can see that the thin wall cells, you can see we had some PFDI inside penetrating into that. But for the vascular, we don't have any existence of the PF or PMDI. I guess it is because it has a higher density. The vascular bundle, it has a higher density, so the glue cannot penetrate into that part, which means that when we remove the green wall shell of the bamboo, we are removing a high density vascular bundle, and the glue can penetrate into deeper layer with a greater binding power, which means that along the width, since there is a pro-grain adhesiveness between the two laminated layers, then it has been highly stable. So the displacement performance along the width is better than the length. And for the dimension and the thickness direction, those containing green wall is better than those without green wall, which means that the green wall is actually has a higher stabilizing ability. So retaining bamboo green in the form of bamboo instead of wood can effectively improve the flexural ability of bamboo wood CLT model. And if you want to reflect the high flexural and tensile ability of bamboo green, it is necessary to improve the intersection strength of the plate and shear ability of the core layer. The design of bamboo as the surface not only avoids the bottom tensile failure of bamboo CLT model, but also makes the size variation of bamboo CLT model lower than that of wood CLT model, which improves the size stability of bamboo CLT model. And the design uses a kind of mixed rubber suitable for bamboo and wood gluing, because in the system, we saw that the anti-shear force ability is not very well. And also, at the same time, when we mixed the different rubber glue, resin glues, we can provide a reliable basis for the manufacturing of orthogonal glulam with high dimensional stability and high strength. Okay, thank you.
Can I ask a question? The density of the Dendrocalamus giganteus, any big difference of this bamboo to other timbers with regard to density? Are you asking about the differences of density? Sorry, I need to put up my slides again. According to the standard CLT recommended, the densities difference should
Hablando en chino, no
more
hay
than
interpretación.
0.35. There is no specific requirement.
Hablando en chino, no
I
hay
made
interpretación.
some comparison on the air dry density. You can see for the Dendrocalamus, it is 0.8. And for the eucalyptus, this is 0.6. So the difference of the density is 0.2. So Dendrocalamus, what is the thickness of the wall? Because I know the thickness of each bamboo segment is limited, right? Because we selected local bamboo species, Dendrocalamus from Yunnan. Relatively speaking, the bamboo wall is around 30. So I'm not sure whether I understood your question correctly. You were talking about some of the bamboos, since the wall is too thin, so it cannot be used. Because for the mossel bamboo, if you eliminate the greener part of the wall, then the thickness is not good enough. Okay, I got your question. Because in my design, I'm designing a very small panel. You can see it's not very thick. So it's 35 or 45 millimeters. Because I understand that for various bamboo species, the wall is very thin. So I split the bamboo poles first, then make use of all of the bamboo poles and develop the smaller panels, because I want to make use of all the segments of the bamboo. We remove the nodes of the bamboo. If you include the nodes, then the length can be lengthened. And if one unit contains 3 layers, then we can glue them together. One CLT with 3 layers, then we can produce a larger panel based on the standardized specification. Okay. There's a question from Jim. Does this apply to all bamboo species used in CLT, whether they have a green or brown outer shell? That it's important to keep the shell. But most companies strip out that shell to make CLT. First part of the question, yes, we can use other bamboo species as well. Previous speaker also presented that in addition to dendrocolumns, other bamboo species are also having very good bending strength, tensile strength. Actually, some bamboo species bending strength is better than dendrocolumns. So you can use other bamboo species as well. And for the timber species, instead of eucalyptus, you can replace eucalyptus with other tree species. Because my study is in Yunnan province, so we use the indigenous species, eucalyptus. The better shear strength the core is, the stronger of the CLT is. The second part, whether to remove the green outer shell. We believe to remove green outer shell, it would cost resources, human resources, and financial resources. Of course, if you can remove the green outer shell, it's better. But dendrocolumns is really wonderful. It has a big hollow in the middle, but very thick wall of the bamboo and high tensile strength comparing to the timber. Since you are all experts, when we conduct tests and study, we all know that the green outer shell, the tensile strength is very good. So if we can keep the green shell, to make use of its good bending strength, because it's coming from nature. It's a nature embedded idea. If we can keep this idea, it would be good. Yes, we can hear you now. Yes. Thank you, Chair. I'm from Professor Yu's team from Chinese Academy of Forestry. I'm very delighted to brief you about the manufacturing technology and engineering application of large-sized directional bamboo laminated lumber. 4 parts of my presentation. The first is development status quo of engineering bamboo-based material. From ancient time, bamboo is a traditional raw materials, including bamboo chairs, bamboo basket, bamboo boats. Nowadays, we use bamboo to produce wind turbine blades. And the most popular bamboo-based materials, including laminated bamboo lumber, bamboo scrimber, flattened bamboo. Previous speakers talk about CLT. Out of all these bamboo materials, I believe bamboo laminated lumber, or LBL, due to its easy process, uniform structure, well processability, it can be widely used for architecture decoration, doors and windows, household products, and floor. LBL has good advantages keeping the grains of the bamboo, but the strength is as good as hardwood timbers. But currently, commercially available LBL length is less than 3 meters. So when we use LBL to produce larger span products like these bridges, it would have some limitation. So how could we make upgrade based on the nature of LBL? Professor Yu, together with a company in Jiangxi, started the study on the large-sized directional bamboo laminated lumber. Traditional manufacturing process started from shaping and lengthening. As a result, it had a very low production efficiency and higher material loss rate, and also low mechanical properties. According to the literature, the largest strength loss is 50%. For the innovative manufacturing process, it started with lengthening step, and then do the shaping, and then produce a large-sized LBL. By using continuous hot pressing technologies, it can produce indefinite length. By doing so, the production efficiency being greatly enhanced, and the loss rate of material is very low, and the mechanical properties of the bamboo being retained. 3 innovative features. First is pre-treatment technology of bamboo strip units, including the hydrothermal synergistic treatment. By doing so, we can extend the durability and the stability of the specification. Second, we use a directional extension with hook joint. and the directional extension technology without glue at the hook joint can improve the evenness and the durability of the products used. We also innovate secondary gluing technology of phenolic resin with different molecular weight. By doing so, we can increase the distribution of phenolic resin in cell wall. By doing so, the tensile strength being increased. We use this hook joint by one-step processing, as well as automatic gluing and staggered assembling model. We do not need a second time gluing at the joints. Through these technologies, we can produce DBLL. It is 1.6 times comparing to the other laminated timber with regard to the expansion rate and also static bending intensity and the specific strength. And the products manufactured had received certain international standardization verification, and also brought direct economic benefits for the companies in recent 3 years, about 120 million yuan. Next part is about the application and the production. You can see on the left-hand side is the experts from the Chinese Academy of Forestry, and right-hand side is our specimen and panels being developed into beams and also landscape architecture. It can also be used for indoor purposes, furniture and other household items, and BMW and Mercedes and Volvo are using our DBLL as their vehicle floor. This DBLL's length is 20 meters. It can be used for large size decoration and to produce larger beams. Has a very good durability and also aesthetically is much better. The prospect of this DBLL development, because DBLL is very much aligned to the Chinese national strategy, that is dual carbon goals. And we can replace plastic with bamboos and to explore greener and low carbon development and make our contribution to a greener planet. Thank you. I have 2 questions. You were talking about gluing, overlay gluing technology. And my second question is this hook joint. Do you have devices or machinery to do so? I didn't hear your first question clearly. Let me answer the second question about the hook joint. Yes, we have the machinery.
We have a knife set. We can have a customized knife set, so you can punch it once, and the production efficiency is very high. Could you repeat the first question? Yeah, the first question, you mentioned the laminated or multi-layer gluing technology. What is that? Because we are using the different molecular weights, like a high molecular weight resin 2000 molecular weight, and because of that, our products is like laminated layers, and if it doesn't really have good penetration, then for a certain portion of, there may be a patch that is missing the glue, and then we have a secondary coating of the glue with a lower level of molecular weight, so we have a multiple layer of glues. So using two resin, yes, two glue layers. The hook joint, in the hook joint, sometimes you may have a deviation and the hook actually would fracture. Would that happen? Because it looks really intricate. You mean when we are processing, right, where we are making the hook? It rarely happens because the four sides, we're using 4 different knives to punch at the same time. So it's intact. In real practice, we don't see any fracture or wear and tear damage at the sides. Okay, thank you very much. So we have a question from Jim. Can you read that? Yes, I understand. For the resort case and the truck case, all those are real life case already using this product. And this company is from China, Jiangxi Anzhu Bamboo Technology Co. Limited, already used. Okay, thank you very much. If you need more detail, you can contact me. I will leave my mailbox. Yeah, you can write to me. I hope you can hear me. Okay, thank you very much. Let me share the screen. So good day, everyone. I'm Lei Wei Cheng. I'm from the Chinese Academy of Forestry, Wood Industry, the Research Institute, Wood Industry. I will talk about 4 things. First, my background. So as a new material, bamboo-based fiber reinforced composite has been widely used in furniture and outdoor buildings due to its high durability, high strength, and it is widely used for outdoor structures. and for landscaping purposes. But when used outside, is subject to weathering, ultraviolet radiation, moisture penetration, and temperature variations. And it will be subject to natural aging. So first, the oxygenation and ultraviolet radiation will have a photoic degradation, and also the moisture-induced degradation. The radiation and oxygenation will wear and tear the surface, leading to surface corrosion, cracking, and other phenomena under the natural aging conditions. And also there are small fractures on the surface. But for the humidity and hydrothermal agent, it will also lead to cracking of the surface. When it cracks, its anti-corrosion and durability will be damaged because the active substance inside the laminated the bamboo screen board will be exposed to external elements, and it will damage the whole screen board layer. So we are using the 1.2 millimeter thickness, and we're using 28-hour cycle to simulate outdoor aging to test its variation of properties. And we are using the ultra high definition scope to detect the cavity change and the crack change. And also we use the infrared to check its chemical changes. With increasing cycles, the water absorption, the swelling coefficient continue to goes up. And at the 7th cycle, the screen board growth is 0. Water absorption and dimension swelling will remain stable. And after the numerical simulation and the fitting formula, we can have forecast of the stability of the bamboo screen board material. We also looked into the forms of the morphology of the bamboo screen board. You can see the area of cell cavity and crack changed sharply in the earlier stage of the cycle and changed slowly in the late stage of the cycle. And also we see cracking of the fibrous cell and the thin wall cells. You can see the two curves are in conformity with the macro level form changes. At around the 7th cycle, all the micro level state will remain stable. We also used the pressurized mercury method to detect the pore diameter changes before and after the cycles. And after cyclic treatment, we have investigated the porosity, total pore area, and the average pore diameter. You can see that after the cycles, all the pore diameters go up. And also we see a very interesting curve here. You can see that all the pores are getting bigger, so smaller pores are getting fewer. You can see that we can see the pore size distribution on these two charts. 5.5 to 30 nanometer will be the primary pore diameter area before the thermal hydrothermal agent cycles. So after hydrothermal aging, the cell cavity increases. And we're using the mercury intrusion porosimeter. It is good for detection of the larger pores, but not for smaller pores. So we're using NMR cryoporometry to analyze the variety of pore sizes of cell wall before and after the cycle. After the hydrothermal aging, you can see in the bamboo screen bowl, the pore diameters continue to expand, which means that after the hydrothermal aging, existing diameters continue to increase, but and also with the dilution and elution of the soluble substances, there are smaller fractures. And also we are analyzing the chemical and crystallization situation and before and after the cycles. And here, this is the axial bond, which means that here there is a peak. The crystallization level has changed. All the peak are at the same time, which means that the hydrothermal agent did not change the monocrystals. It just changed the crystallization level. And also we are using XPS to analyze the crystal structure of BFRC. And with the OC ratio, you can see that after the hydrothermal aging, the oxygen atom content increases, which means that the surface has undergone oxygenation process. And we have the eluted soluble content and lignin, and they are actually eluted from the bamboo screen bowl structure, which means that the lignin has decomposed in the process of hydrothermal aging, and lignin is more susceptible to hydrothermal aging than cellulose. So we conducted 27 cycles of hydrothermal drying and hydrothermal treatment of BFRC. After accelerated aging, the dimensional stability, the pore structure, the micromorphology, and the chemical composition of BFRC has changed. The fibrous cells, the thin wall cell interface may fracture, and the cavity of the pores have increased. Fracture has occurred. So the macro dimension of the bamboo screen bowl has swollen. And also we analyzed the chemical composition. Both cellulose, semicellulose, and the lignin have decomposed, which means that not only the physical structure, but also the chemical composition have all changed.